In this part of 5.1, we're going to talk about whether a sequence converges or diverges. So remember, if it diverges, it's going to infinity or to negative infinity. If it converges, it's going to some value. So we're looking for some value. So definition, we have a sequence a sub n, and it has a limit as n goes to infinity. If the limit as n goes to infinity of a sub n exists, has a value, then it converges. If the limit as n goes to infinity of a sub n approaches infinity or doesn't approach a value, then the sequence is said to diverge or is divergent. So we can look at some graphs. That sometimes is very helpful to see what's going on. Using a graph to look at a convergent or a divergent sequence. Convergent sequences approach some value as n goes to infinity. You can see this in the graph. So looking at this graph over on the right side, if I'm looking at this graph as n is going to infinity, what's happening to my value of my graph? It seems that it has a horizontal asymptote at y equals 1. So we would say that this graph, as x goes to infinity, approaches 1 or converges to 1. So looking at some stuff that we've known from previous courses, as in a college algebra class, we can use some limits to find algebraically about what's happening, whether a sequence converges or diverges. We can use L'Hopital's rule from Calc 1. We can use other ideas of limits that we understand from Calc 1. We can also use end behavior from a college algebra class when we're talking about a rational function. So if I have some fractional function, I can use hopefully what I might remember about end behavior or the horizontal asymptote test. Okay, so talking about the horizontal asymptote, here I have a rational function, and we look at the degree of the top or the degree of the numerator versus the degree of the denominator. And if they're equal, as in the degrees are both 4s, this will converge to the leading coefficient, the coefficient in front of those highest terms. So this would converge to 5/6. If the degree in the numerator is greater than the degree in the denominator, so 4 is greater than 2, then there is no horizontal asymptote, and the limit as, not x, the limit as n goes to infinity is equal to infinity, so we would say this diverges. And the last example, the last horizontal asymptote that we look, if the numerator is less than the denominator, so this numerator has degree 1, this denominator has degree 2, this would have a horizontal at y equals 0, so it would converge. Then using L'Hopital's rule, we might want to remember some of the forms of L'Hopital's rule. So we really want to have a 0/0. We could have infinity over infinity or 0 times infinity. These are all what we call indeterminate forms. So we're going to look and see what happens. We'll use L'Hopital's rule here. It says, find the limit as n goes to infinity of n squared over e to the n. And if I plug in infinity, I get infinity squared over e to the infinity. Well, infinity squared is just big, and e to the infinity is just bigger. So we really just say this is infinity over infinity. So it's an indeterminate form. It's one of those forms, and these are the two forms that we like, 0/0 or infinity over infinity. So we can use L'Hopital's rule that says we take the derivative of the numerator and the derivative of the denominator separately. So we would have the limit as n goes to infinity of the derivative of the numerator is 2n and the derivative of the denominator is e to the n. If I plug in infinity again, I get infinity over infinity. So I have to repeat L'Hopital's rule one more time. And if I repeat L'Hopital's rule again, I get the limit as n goes to infinity of 2 over e to the n, which is 2 over infinity. And we remember if we divide any number by something that's really super, super big, we're getting 0. So we would say this converges to 0. So let's look at some geometric sequences. We looked at some before. A few things that we talked about before, but just a little reminder. Here's that formula for a geometric sequence, and I said before you could look it up, where r is the next term divided by the term before it. And so we can look and say, well, this thing has a common ratio right here. We're multiplying each number by 2. So our common ratio would be 2. Here, if we did our a sub 1 and our a sub 2, and we did 2/3 divided by 1, that common ratio would be 2/3. So that's just getting the common ratio. Well, why would I want to know the common ratio? Well, we'll find out that if I have a geometric sequence, it will converge if my common ratio is between -1 and 1. So just looking at these examples up above, this one would converge. This one right here is not between -1 and 1, so the first one would diverge. Let's think about what we call the squeeze theorem. You've seen the squeeze theorem in a calculus problem, and a lot of times when we first do this, everybody goes, oh my God, how do you know what to squeeze it between? Well, when I'm looking at this example right here, a couple things help me realize this. So I want to use the squeeze theorem to find the limit of the sequence cosine of n over n squared. Well, I'm going to think about what we know. We know that cosine is always between -1 and 1. The values are always between -1. They're bouncing -1, 1/2, square root of 2 over 2, square root of 3 over 2, 0, 1, all of those numbers, right? So I have an n squared on the bottom. So what I'm going to do, I'm going to make my problem look like that. I'm going to multiply the whole thing by n squared. I'm going to get -1 over n squared is less than or equal to the cosine of n over n squared, which is less than or equal to 1 over n squared. So now what I want to do is I want to see, does that have a limit? And does that have a limit at infinity? So let's look at both limits separately. So let's do the limit as n goes to infinity of -1 over n squared. Well, if I put infinity on the bottom, I have -1 over a really, really big number, which is 0. So that side's converging to 0. What's happening on the other side? So on the other side, we have the limit as n goes to infinity of 1 over n squared. This time it's a positive 1, but it's not going to make any difference because I'm still going to have 1 over a really big number, which is 0, which means that right here, this is being squeezed between 0 and 0. Well, if it's being squeezed between 0 and 0, it's 0. So we can say that the limit as n goes to infinity of cosine of n over n squared is equal to 0. So lots of different ways here that we can do this. Looking at my first one, if I notice it, I tend to use L'Hopital's rule a lot. So I notice this one, if I plugged in infinity, because remember what we're doing, we're taking the limit as n goes to infinity of 3n over 1 plus 6n. I'd have a really big number over a really big number. So if I use L'Hopital's rule, I'd have 3 over 6, or this thing is going to converge to be 1/2. I could also think about this as a horizontal asymptote, and both of these powers are the same, so it is the leading coefficients. Looking at example number 2, I have 1 plus 10 to the n power over 9 to the n power. So when I have an addition here, I'm going to want to split these. So I want to take the limit as n goes to infinity of 1 plus the limit as n goes to infinity of 10 to the nth power and 9 to the nth power. Well, this thing I could think about as some sort of exponential growth. And if I think about it as an exponential growth here, I could say 10 over 9, they both have the power of n. Well, what's going to happen to this? Doesn't matter. N, if I plug in infinity, this thing's just getting big anyway. I could think about this as big over big. Doing anything else here, it's just going to infinity. So I'm having 1 plus infinity, so this thing is going to diverge. Let's look at example number 3. I have 2 minus 0.3 raised to the nth power. Okay, so again, we could do this by splitting it, going the limit as n goes to infinity of 2 minus the limit as n goes to infinity of 3. I'm going to write that as 3/10 to the nth power. Well, we already said, oh, this one's a little different because this is 3 over 10. My bottom number is bigger. So the bottom is getting bigger. This thing's going to go to 0 because my bottom's getting super big. My top's not getting as big. So therefore, this is 2 minus 0, or this thing converges to 2. I can also think about this as an exponential, let me say a little bit more here, decay. And if I'm looking at an exponential decay, I know that it's going to 0. It's decaying down to 0. Remember those exponential decays? They're looking like this, and they have that horizontal asymptote at 0. This one over here was a growth. And that's because this number is bigger than 1, and this number is less than 1. So a growth, it's going up. Just thinking about the couple of different things here. Here I could use L'Hopital's rule on number 4, or I could use some sort of horizontal asymptote, which is what I'm going to do. So usually if I'm using a horizontal asymptote, since that has a root in it, all I do is take the square root of that first. So it's 4n over 3n, which is going to converge to 4 over 3. What happens now if I have factorials, right? Factorials can be a little crazy. Hopefully we remember like 5 factorial. What does that mean? 5 times 4 times 3 times 2 times 1. Well, and then remember that 0 factorial is always equal to 1 because that's kind of a weird thing. So let's write a few of these terms out. It may be helpful. We may notice something is happening once we write them out. So we would have 3n minus 1. The next term after that would be 3n minus 2 because remember you're subtracting 1 from each term. Then we would have 3n minus 3. And you could think that I'm going all the way down until I have 3 and 2 and 1. All right, now what's happening in the denominator? I have 3n plus 1. I'm going to subtract 1 from that. I'm going to have 3n. I'm going to subtract 1 from that. I'm going to have 3n minus 1. And subtract n from that and 3n minus 2. And I would just, maybe I'll do the next one so you can see it. And then I'm going down to 3 and 2 and 1. So now, cancel everything out in the numerator and the denominator. This is why we love factorials. The 3n minus 1 cancels out, the 3n minus 2, the 3n minus 3, and all of the dots, and 3, 2, 1, 3, 2, 1. And 3, 2, 1, 3, 2, 1. Everything canceled out. What was I left with? 1 over 3n plus 1 times 3n. And if I plug infinity into that, remember I'm taking the limit as n goes to infinity. If I plug infinity, I get 1 over infinity, which is 0. So this thing is converging to 0. Let's look at sine of 3n. So this is the limit as n goes to infinity of the sine of 3 over infinity. Remember, you're just plugging the infinity in for the n. 3 over infinity is 0, so this is the sine of 0. Well, the sine of 0 is equal to 0, so it converges at 0. Let's look at number 7. On number 7, we have the sine of n over n cubed. So we're doing the limit as n goes to infinity of the sine of n divided by n cubed. Well, we know the sine of n. What do we know about that, right? That's between -1 and 1. I don't know what the value is, but I know it's between -1 and 1. And then I have infinity raised to the third power. Just infinity getting bigger. So I'm dividing some number between -1 and 1 by some really big number, which gives me 0. So this converges to 0. So what if you notice, we're doing the same thing every time. We're taking the limit as n goes to infinity of 2 plus 3n to the nth power. Okay, let's plug in our infinities. So we have 2 plus 3 over infinity to the infinite power. Well, that's 2 plus 0. 3 over infinity is 0. So 2 to the infinite power. That's just getting big, right? So since it's getting super big, that's a growth. And that thing diverges. It's going to infinity. So diverging means it's going to infinity or it's going to negative infinity. How about on number 9? Let's take the limit as n goes to infinity of 1 plus 1 over n to the nth power. Well, this one is a little different maybe. This is 1 to the infinite power, and we said 2 to the infinite power before diverged. But this one, I'm not sure. I mean, we did a little bit of math to that one to look at it. And we had a little bit more going on in that other problem. Here we have 1. This is an indeterminate form. We have that 1 to the infinite power. This is an indeterminate form. So I'm going to take the ln of both sides here. Remember, I have a y equals. So I'm going to do the ln of y is equal to, and we're going to do the ln on the other side. So we're going to have the limit as n goes to infinity of the ln of 1 plus 1 over n to the infinite power. Oops. 1 plus n to the nth power. Let's pull that n out in front. That's a logarithmic rule. So we end up pulling the n out in front. The limit as n goes to infinity of n times ln of 1 plus 1 over n. We'll use, well, this is still an indeterminate form here because now we have infinity times 0. And we like to have 0 over 0, so we're just going to put that n in the denominator. So we're going to have ln of y is equal to the limit as n goes to infinity of ln of 1 plus 1 over n all over 1 over n. So that's what I did with that n. I brought it down and I made it 1 over n. Now we have 0 over 0 and we can use L'Hopital's rule here. So let's go ahead and use L'Hopital's rule. And if we use L'Hopital's rule, I'm going to do the derivative of the numerator. So remember, we have ln of y is equal to the limit as n goes to infinity. We're doing the derivative of the numerator, which is 1 over all of that stuff. So I'm going to put that stuff on the bottom. And then the derivative of 1 plus 1 over n, which is -1 over n squared. So there's the derivative of ln, and now we need to do the derivative of the denominator. So that was the derivative of the numerator, and the derivative of the denominator, 1 over n, is -1 over n squared. So now what happens? Those -1 over ln squareds, those -1 over n squareds cancel out, and I end up with ln of y is equaling to the limit as n goes to infinity, that should be an infinity there, of 1 over 1 plus 1 over n. Well, let's plug in infinity here, and that's going to make that 0. So we're going to have ln of y is equal to 1. Take e to both sides. E and ln cancel out. Y is equal to e to the first power. So this thing is converging to e. Let's do the last one in this section. The limit as n goes to infinity. So let's do the limit as n goes to infinity. And we're going to, if I plug in infinity here, I have infinity minus infinity. So I'm going to use my log rules and I'm going to divide those. So I'm going to have 2n squared plus 1 over n squared plus 1. Now, just on the inside here, I'm going to use my horizontal asymptote rule. And if I use my horizontal asymptote rule, the inside of that is going to be 2. So that means I have the limit as n goes to infinity of ln of 2. So that converges to ln of 2. On this last bit that we're looking at in 5.1, we're going to talk about alternating sequences. So when we're talking about alternating sequences, we're talking about alternating their signs. If their signs are alternating. If we take the absolute value of all of the terms, we're going to get 0. If we add them all up to infinity. It's really super easy, and when that happens, when that happens, we say that it converges to 0. So if we get 0 when we're doing the limit as n goes to infinity, then it converges to 0. Otherwise, it diverges. Any other value, it's going to diverge. Okay? So let's look at just a couple of quick examples. I have 2 and negative 2 and 2 and negative 2 and 2 and negative 2 and 2 and negative 2. So you can see these are all going to cancel out and this thing's going to converge to 0. Okay? In the next one, this is alternating, but I don't know if this is going to go to 0 because, I mean, these numbers, I don't think that they're going to give me 0 if I add them up. So this one is going to diverge. So let's look here. This is just telling me that it's an alternating sequence. I'm really going to look at the limit as n goes to infinity. We're just going to use 1 on the top because it's alternating between 1 and negative 1, and we want the absolute value of that, so that's 1. And then we'll have n to the 1/3 power, or 1 over infinity to the 1/3 power. Well, it doesn't matter if it's infinity or infinity to the 1/3 power. It's still big. 1 divided by a big number is converging to be 0. So it's converging. Let's look at the last example that we have here. In our last example, here is the alternating portion of it. We don't need the alternating portion of it. We're really just going to look at the limit as n goes to infinity of n over n plus the square root of n. Let's go ahead and use L'Hopital's rule on this and take the derivative of the numerator and the derivative of the denominator separately. So we end up with the limit as n goes to infinity of 1 over 1 over 1 plus n to the 1/2 power is 1 over 2 square root of n. Plug in infinity, we have 1 over 1 plus 1 over infinity. This is 0, so we have 1 over 1. Well, what do we say about 1 over 1? It's not converging unless it's going to 0. So this diverges. Diverges because it is not going to 0. There's other sequences that we're really not going to talk about here, but they're worth looking into at some point in time. So the Fibonacci sequence, some of you might be familiar with that. You need the first 3 terms, 0, 1, 1, and then you're adding the 2 terms before. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. So that's the Fibonacci. And you could look at that one. There's also a golden ratio, 1 plus the square root of 5 over 2. And that limit is actually phi. So that's the golden ratio. And we're not going to look at either one of those, but they're interesting ones if you do want to look into them at all. So that is the end of 5.1, and I will see you in 5.2.